Namaste everyone. This is Vinay Kumar. Today I am going to talk about hyperspectral remote sensing, an overview and applications. So in this case, you can see there are three images I have shown to you. One is that how the hyperspectral data acquisition is taking place. Second, one of the FCC image generated from hyperspectral data. And third is the classified image of hyperspectral data. Now the name itself, the name of this is called what? Hyperspectral. So here what we are doing is we are focusing to the spectral. Spectral means, as you know, that there are four types of resolution: spatial, spectral, temporal, and radiometric. So spectral is deciding, or it is talking about that how narrow spectral bandwidth is, and because of that narrow spectral bandwidth in the entire wavelength region, that is visible to reflected infrared region. So if you have more number of spectral bands, then you can have a better spectral reflectance curve. Because you know that if you have to identify any of the feature, or if you have to differentiate any of the feature, then you require a detailed spectral reflectance curve. So hyper means what? Excessive. Excessive number of spectral bands in remote sensing is your hyperspectral remote sensing. So in this case, you are going to see how hyperspectral data has many number of bands and narrow bandwidth, and how it is little different from your other multispectral data processing. And some processing will be similar, but many things like classification techniques for hyperspectral data are going to be different. So you can see here, as I talk to you about your spectral reflectance curve, you can see the major three land cover features are your soil, your vegetation, and water body. So if you have to differentiate between the different data, like depending on spectral resolution, there are three categories of the data: panchromatic, multispectral, and hyperspectral. Panchromatic is a single band data which is ranging from visible to near infrared or visible wavelength range is being used. So that is called as your single band data, which is a grayscale image. And if you have to differentiate various features, you can differentiate by seeing the grayscale image. So if some feature which is having lesser reflectance, they will appear darker. And if it is having higher reflectance, then it will appear brighter. Then multispectral data is what? When you have further subdivided that bands into discrete bands like blue, green, red, near infrared, and short-wave infrared range bands, then you can get the nature of particular feature, like this may be vegetation, this may be water body, and you can generate color composites out of it to identify any of the feature. But in case of hyperspectral data, you have continuous spectral bands from visible to reflected infrared range, and continuous reflectance observation is being done through different bands. Now, because of you have continuous spectral bands, you can get the absorption feature. Like here, we can differentiate water, vegetation, and soil by seeing the absorption present in the reflected infrared. You can see that water has low reflectance in visible region, but in infrared region, it is negligible. In case of vegetation, you know that green has high reflectance and red has absorption, and near infrared has high reflectance. So this may be vegetation. And in case of soil, it is kind of continuously increasing, and kind of constant reflectance is there. So that's why they appear brighter in your FCC images. Now, if you have to identify the different species, like different vegetation species, then how we can do that? By looking over the FCC image, we can tell that this red color will be vegetation. But which vegetation species, if you have to identify that, then you require hyperspectral data. Like for example, you can see there are two mineral features, minerals here shown, and in this particular wavelength region, you can see the absorption, diagnostic absorption features are present, which can be differentiated when you have your hyperspectral data, because you are going to get detailed spectral reflectance curve of the feature. Now, how we are going to get that? So first we have to understand what is the definition of spectral resolution. So spectral resolution is defined as the ability of an instrument to separate light into finite distinct wavelength region and distinguish these finite regions from each other. So this is also termed as full width half maximum of the spectrometer response to a monochromatic source. So you can see here, this is the spectral response of one particular single band. Here, what is considered as, this is particular for this particular detector, this is the 50% response and this is the full width. So this particular full width half maximum is called as the spectral bandwidth of the channel. And depending on this spectral bandwidth and how frequently the particular spectral channels are being observed, they are called as sampling interval. So you can see here this detector response for this particular band, this particular band, and this particular band are kind of continuous, means there are no gap between these three particular bands. Now, if you want to see the spectral response function, if you have to see, understand the spectral resolution, you have to know what is spectral response function. So this is called as spectral response function. The other name of this spectral response function is relative spectral response filter function of that particular bands. So here you can see, this is the spectral response. This black color plot is for panchromatic sensor, which is considering the visible to near infrared band as a single band, visible to near infrared range. Now you can see with different colors, blue, green, red, and near infrared wavelength region, how discrete these bands are from each other. And there are some, in this case, it is having no gap between the blue and green band, but in other case, you can see that there are gaps between the bands. They are broad spectral bands in case of multispectral. But spectral response function of hyperspectral sensor will be something like this, which is continuous from visible to reflected infrared region, and there will be no gap between the bands. And for each particular band, we are going to get the reflectance value from the Earth's surface. So that's why the spectral reflectance curve will be in more detail in case of hyperspectral data. Now, coming to the difference between multispectral and hyperspectral data. Multispectral sensors have discrete or broad spectral bands. Hyperspectral will have contiguous or narrow bands. Contiguous means it is going to cover the wavelength range, and narrow bands means between each and every single band that is very, very narrow. Like for example, if I'm going to talk about wavelength range that is blue, that is from 400 to 400 or 400 to 500 nanometer. But in case of hyperspectral will be 400 to 410 nanometer, 410 to 420 nanometer, 420 to 430 nanometer. So 10 nanometer will be your spectral bandwidth. So that's why they are narrow. And contiguous means if it is covering the wavelength range and from each other, from different bands, there will be no gap. Multispectral instruments can discriminate materials. That's I have shown through your particular spectral reflectance curve, like water, vegetation, soil can be discriminated. But if you have to actually identify the material, you require hyperspectral data. Multispectral data are used to detect the existence of various materials, but hyperspectral data allows identification of many materials even in mixed materials. Suppose if it is a mixed pixel, in that mixed pixel you can identify the more than one particular feature present in that. So that can be distinguished. Greater accessibility because larger number of space-based multispectral sensors are there, but very few hyperspectral sensors are available. So you can see here with multispectral data how discrete bands are appearing, and because of this continuous spectrum, how the data will be there. Now, in this case, you can see there are three data sets I have shown to you. Landsat 7 ETM Plus with 6 multispectral bands, EO1 Advanced Land Imager sensor, which is with 9 multispectral band, and EO1 Hyperion data with 150 bands after pre-processing. So you can see this is showing me the nature of vegetation, like high in green, absorption in red, and very high in near infrared. So this is vegetation. Now you can see sudden absorption we are getting in this case of 9 spectral bands. But when we have hyperspectral data with more number of bands, you are seeing the continuous absorption. So because of this absorption, you can tell that which kind of vegetation species this would be. Now coming to the imaging spectroscopy, so you have to understand the three particular this triangle. There are three things here: imager, spectrometer, and radiometer. Imager is what which is going to provide you two-dimensional image of any area, that is spatial information. Spectrometer is a device which measures the spectral distribution of electromagnetic radiation, and radiometer is an instrument which quantitatively measuring the intensity of electromagnetic radiation in some band of wavelength in any part of electromagnetic spectrum. So when we combine spectrometer and radiometer, this is a non-imaging device which measures the radiation in different wavelength region. So that is useful for measuring the spectral reflectance curve of any particular target. Now, when we combine with the imager, that is called as imaging spectroradiometer, which gives me a two-dimensional image, as well as for each pixel, it is going to give the spectral reflectance curve. Now, how we are going to get that particular number of channels? If you remember the difference between whisk broom and push broom scanner, in that case, for multispectral sensor, we have different detectors for different bands like blue, green, red, near infrared, short wave infrared. But in case of hyperspectral data, launching 200 detectors for different channels is a difficult task. So in place of that, people are using different kind of technology to do the spectral separation. Like for example, people have done exercises during school time that whenever we are using a prism and we are passing a monochromatic white light, then spectral separation takes place. So there are many ways for doing the spectral separation, which are diffraction grating, wedge-based filter, Fourier transformation filter. So there are many filters being used for doing the spectral separation. So by using this technology, we are doing the spectral separation and we are getting the spatial information for that particular band. Now, the other name of hyperspectral remote sensing is imaging and spectroscopy. So spectroscopy first is called as what? Whenever electromagnetic energy interacts with any of the target, depending on physical and chemical characteristics, some are getting absorbed, some are getting transmitted, and some are reflected. So to understand the particular principle of the interaction of electromagnetic radiation with the particular object, so that is called as spectroscopy. And when we combine with the imaging, that is called as imaging spectroscopy. So as these two are combined, it includes large data sets because it is having more number of spectral bands and it requires new processing method. So normally this acquisition of data are having many contiguous spectral bands and ultimately producing laboratory quality reflectance spectra. So whatever data we are acquiring, we have to convert it to surface reflectance. And after converting it to surface reflectance, this particular pixel is indicating the reflectance curve of the feature. So this XY is representing the spatial information and this Z is representing the spectral information. So normally it consists of 100 to 200 spectral bands with a narrow bandwidth of 5 to 10 nanometer. Now we have data sets with more than 400 bands with 5 nanometer spectral resolution. Now coming to whenever you have more number of spectral information, the spectral information will be more, then you can actually identify the material and can distinguish the feature. So by you can see here the data cube is represented here, where the band combination used for the FCC is band 40, 30, and 20. It means that near infrared band position is 40th, the red band is in 30th band, and your green band is in band number 20. So that's why the band combination is then only it is going to show the FCC. So now you can compare with multispectral data. The band combinations are normally 432 or 321 depending on the sensor. Now here we are using 40, 30, and 20 in case of Hyperion sensor data. Now, why we are using hyperspectral remote sensing? So as I already told that most of your Earth surface materials have are showing absorption feature in this visible to reflected infrared region, and that these absorption features are very, very narrow, and this can only be detected when you have data with high spectral resolution. So here you can see there are two minerals, alunite and kaolinite. So this particular absorption and this steep slope, whatever we are seeing in these two minerals, are only visible when you have a hyperspectral data. So to identify any feature, any mineral, hyperspectral data are very, very useful. Now, there are different types of absorption features: charge transfer absorption, electron transition absorption. So normally these two are electronic processes and another is your vibrational process. So charge transfer absorptions normally occur in the visible region of the spectrum and caused by light at certain wavelength, causing electrons to be transferred between atoms. So one example is your from Fe2 plus to Fe3 plus, whatever charge transfer is happening, that is causing your iron objects are getting rusted when it is exposed to your air or moisture. Now coming to electron transition absorption, it is narrower than your charge transfer, and in this case atoms with an incomplete electron cell, light at proper wavelength can bump electrons into different positions in the cell. So it is narrower than charge transfer and especially useful in geology. Vibrational absorptions, when light at same wavelength as a molecule or part of molecule strikes the molecule, it causes the molecule or part of the molecule to vibrate. So these absorptions are very, very narrow and actually originate at longer wavelength of the wavelength region visible to reflected infrared. That means short wave infrared region. So mostly useful for identification of different types of minerals. So you can see here, these are the various absorption positions which are observed for different minerals: quartz, gypsum, montmorillonite. So how these absorptions are visible over here. Now, requirement of spectral resolution is dependent on the width of occurring absorption. So for soil and geological applications, mostly near and short wave infrared with 10 nanometer resolution is necessary. Like for iron bearing minerals, carbonates, sulfates, 0.4 to 1.4 micrometer. Carbonates, hydroxyl group of carbonate, phyllosilicates, clay, this 1.5 to 1.85 and 2 to 2.5 micrometer is sufficient. For vegetation, you can see the chlorophyll pigment can be detected in your visible region, 0.43 to 0.65. Plant water, cellulose, protein, starch, lignin, starch, protein, nitrogen. So this can be detected in 0.9 to 1.4 and 1.4 to 1.9 and 2 to 2.4 micrometers. For snow and ice, like snow grain size mapping, snow depth, contaminants, snow grain size, liquid water content, 0.4 to 0.8 and 0.8 to 1.4 micrometer is sufficient. Now, coming to determination of soil moisture, less than equals to 50 nanometer in short wave infrared region. Weak absorption bands of carbonates, dolomite and calcite, 1740 nanometers, 1760 nanometer, and 10 nanometer spectral resolution is sufficient. Now coming to different minerals, as I told, that short wave infrared region, that is longer wavelength and visible to reflected infrared, 2000 to 2400 nanometer is sufficient with 10 nanometer spectral resolution. Now coming to different hyperspectral sensors. So they are normally categorized into three, that is airborne, spaceborne, and your ground-based. Now coming to airborne sensors, that is CASI is from Canadian technology. In that compact airborne spectrographic imager is there. HiMap, IIRS was one of the technology. Recently, IIRS next generation came. So that is moved from 10 nanometer to 5 nanometer spectral resolution. AHIC is your Indian technology. In case of spaceborne, Hyperion compact high resolution imaging spectrometer, HICI and HICIS are from India. Prisma is from Italian Space Agency. And these are future missions, that is NMAP, HISPRI, that is from German Space Agency and NASA. And Hypersat is going to be constellation of high resolution hyperspectral imaging, which is with 200 plus band with sub 10 meter resolution. So they are going to be low Earth orbit satellites. Now coming to this airborne hyperspectral imager, normally it started with profiling hyperspectral sensors, like they were used for getting the spectral profile, like spectroradiometer were placed and spectral profiles were collected. Then they have launched the imaging spectroradiometer, and it was first launched with 3 different spectral range and different spectral resolution. Then after IIRS was the major technological evolvement which happened in hyperspectral technology, which was used for mineral application. So it was with 220 spectral bands and 10 nanometer spectral resolution. And as they are airborne platform, they can fly with different altitudes to change the spatial, because spatial resolution is dependent on the altitude of the sensor. Then compact airborne spectrographic imager, you can see only visible to near infrared region are being used with 288 spectral bands. Then high map with 400 to 2500 nanometers. So most of your sensors are using 400 to 2500 nanometers wavelength region and spectral resolution of 10 nanometer, but some are varying. Now coming to the spaceborne hyperspectral imager, that Maris is with 410 to 1050 nanometer. Hyperion was one of the sensor which is with very good resolution, which was launched in 2000. So this is containing 220 unique spectral bands with 400 to 2500 nanometer and 10 nanometer spectral resolution and 30 meter spatial resolution. And here you can see the swath width was very narrow, that is 7.5 kilometer. So only small area was getting covered to your Hyperion data. Then HIC on Indian Mini Satellite 1, HISIS, which was launched recently from ISRO, which is with 60 bands in VNIR, 256 bands in SWIR, with 10 nanometer spectral resolution and 30 meters spatial resolution. Then coming to Prisma, which is with 400 to 2500 nanometer spectral range with 237 bands and 12 nanometer spectral resolution. And 30 meter is its spatial resolution, 30 kilometer its swath width. Now coming to different extraterrestrial hyperspectral sensors. So Chandrayaan-1, HIC, Chandrayaan-1 Moon Mineralogical Mapper, Omega and PRISM are from your one of the MRO, Mars Reconnaissance Orbiter. Then MOM is having thermal infrared imaging spectrometer. Chandrayaan-2 is having imaging infrared spectroradiometer. So you can see here the wavelength range are varying. So in this case, it was using 800 to 5000 nanometer with 256 spectral bands and less than 20 nanometer spectral resolution. Now, future hyperspectral missions are INMAP, as I told, that is from German Space Agency. FLORIS is from European Space Agency, and HISPRI is from NASA, and SALOM is from Italian Space Agency. So you can see here the spatial resolution is around 30 meters, and for this France hyperspectral sensor, it is going to be with 8 meters spatial resolution, and this Italian sensor will have 10 meter spatial resolution, but the launch date is yet to be decided. Now, this is the IIRS NG next generation mission. The ISRO and NASA have collaborated, and the data was acquired for different sites of India. So this was with 425 bands and 5 nanometer spectral resolution. So IIRS was with 220 bands and 10 nanometer spectral resolution. So this was the improvement done with your IIRS next generation sensor. Then HISIS was these are few of the hyperspectral images shown from HISIS data, which is having VNIR 60 bands and SWIR with 256 bands. This is the Chandrayaan-2 IIRS sensor, so which is with 0.8 to 5 micrometer and less than 20 nanometer. So this was used for detection of hydroxyls and lunar mineralogy. Now coming to ground spectroradiometer and their specification. So normally these spectroradiometers are used for collecting the spectral reflectance curve. So these are 3 different companies spectroradiometer, that is from ASD, then this is from APOSI, and this is from SVC HR1024 spectroradiometer. Now, coming to the processing of hyperspectral data. So this is the standard hyperspectral data processing. Normally, hyperspectral data is available in radiance form. So this needs to be pre-processed with sensor and atmospheric correction. Sensor means they are having some bands which are containing no information. Some bands are with dropline error. So this needs to be corrected. Then coming to atmospheric correction, so this needs to be converted to surface reflectance. After converting it to surface reflectance, like for taking training signature from this data, the process is little different here. In this case, we have to extract end member extraction. So one of the essential part of this end member extraction is we have to go for data dimensionality reduction, or some of the unmixing techniques required data dimensionality reduced components. Then we have to go for spectral unmixing and mapping. So with the end member extraction, we are going to get this type of spectral libraries, spectral profiles from the data itself, which we can compare with the ground information, and we can go for unmixing and classification. So this I'm going to tell one by one. So first you can see we have to go for bad band and bad column removal. So this kind of no data band will be there. So that needs to be removed. They are absorption bands and noisy bands. And some of the bands will be having drop line error, which needs to be corrected by doing the averaging of the nearest neighbor pixel. Then coming to atmospheric correction. So we have to do the conversion to surface reflectance by doing two approaches, one by empirical and one by using radiative transfer models. So normally empirical approaches are being used when we have no information, no parameters about the data. Then we can go for this. So this is flat field is something like when we have radiance data and we have to identify some areas which are flat, means which are suppose like barren land or bare land is there, which is highly reflective. So we have to consider the average of those pixels of that flat field, and we have to divide from each and every pixel. That is flat field correction. IIRR is internal average relative reflectance. In that case, what we need to do is, normally this works best when we have no vegetation. So we have to take the average of all the pixel value present in that, and we have to divide from each and every pixel. Third empirical approach is empirical line. In this case, we require ground measurements also, means reflectance from ground data. So what we have to do is we have to take the spectral reflectance of two objects, dark and bright, and same thing we have to take from your image itself. So we have to solve a linear equation like y is equal to ax plus b, where we have to consider, like we have to calculate the coefficients like a and b, where x is the dark and bright will be replaced by dark and bright, which is from image, and y dark and y bright is from the image. So by solving that, we can calculate a and b, and then we have to place that in the same linear equation y is equal to ax plus b. So a and b calculated from by using dark and bright will be replaced here, and in place of x we can place your radiance image. So by using that, we can convert that data to relative reflectance. Coming to absolute atmospheric models, in this case, we require various information like atmospheric condition, or date of acquisition and time of acquisition, then what is the aerosol label, what is the water vapor condition, what is the the temperature. So there are various things we have to consider for converting it to surface reflectance, like scene sensor geometry. So by using that, we can convert that to absolute reflectance. So this is the data which is corrected through your flash model, that is using radiative transfer model MODTRAN. So you can see how the reflectance curve is there for different features like vegetation, water, and your urban. Now coming to the third step is data dimensionality reduction. So normally data dimensionality reduction we have to do for subsetting the spectrum of interest. reduce computational overhead, because the processing of 200 plus bands is quite time consuming. So we have to reduce the bands to some number of components. So that can be done through your data dimensionality reduction. Third is reduce the noise, because some of the bands are containing noise. So signal to noise ratio of the data will be removed by doing this particular data dimensionality reduction. So normally three types of data dimensionality reductions are there, which I'm going to explain. There are many, but I'm going to explain these three: principal component analysis, minimum noise fraction, and independent component analysis. So in case of principal component analysis, normally we are transforming the component to transforming the number of bands to the number of components by going for the by translating it to a new origin, which is the mean of, suppose we have two band and we have plotted a scatter plot, then in the mean of that will be calculated. So we have to translate the axis and we have to rotate as such that the major axis of that will be considered as first component and the minor axis is considered as the second, and then so on. So that is talking about principal component analysis. So you can see here, these are the principal components generated from the data, hyperspectral data. So how the first component, second, third, but in this case, there is some problem, because whenever we are doing the data dimensionality reduction with this technique, the noise present in the data will come in between the components. So you can see here 1, 2, 3, 4, 5 is informative, 6 suddenly become noisy, and 7th is a little better, then 8th is better. So you can see in between that noisy component can come. So that's why we have to find, you have to go for some other alternative, other data dimensionality reduction technique that is called as MNF. So MNF component is something like we are applying PCA twice. First to do the noise reduction, and second to generate the number of the components which are noise free enough. So in this case, we are using shift difference method. In this case, what is actually happening is, like we know that nearest neighboring pixels are containing similar signals, but noise content may vary. So we have to do the differencing between the nearest neighbor pixels by using the shift difference method, and the noise component are getting calculated. So using that, we can do the noise reduction, and then we are generating the MNF component like this, which are following the same trend, that first is informative, and then as the number of components will increase, the noise will increase. Then coming to independent component analysis. In this case, what is happening is, we are we can compare with a simple example, that we are listening to a music, and whenever we are listening to music, if you listen to that carefully, you are able to separate out the sound from different type of musical instruments. So same principle is being applied here to separate out different kind of signals from the data by using this independent component analysis. And for this, we are using higher order statistics like skewness and kurtosis for generating this independent components. So here you can see how different features are getting highlighted in this particular different number of components. Now coming to the end member extraction. So end member extraction is a kind of average spectral signature of a pure surface cover type. So this represents a class that have to spectrally classify or identify in the image. So average spectral signature of a pure surface cover type from the image, or how can we get this three? So there are three ways to get that. From field, so you can go to the field with the instrument, can collect the spectral reflectance curve, and can use it for your further application. From spectral library, so there are various spectral libraries which are already prepared, so that spectral libraries can be used for your applications. Then third is what? From image. So from image, we have to run few process for getting the pure end members. So that steps are called as MNF. So that is one of the data dimensionality reduction that I told. Then we can go for PPI, that is pixel purity index, that is for getting spectrally pure pixel locations. Then ND visualizer. ND visualizer means whatever pure pixels are identified, they are putting we are putting into the scatter plot, and then we are extracting the pure pixels which are appearing at the extreme, and we are extracting it. So these are the end members. These are the spectral library collected from the spectroradiometer, and how it is collected from the image that I'm going to show. So here, as I told, that MNF step I already explained. PPI is to get the most spectrally pure pixel location. So this is the data with MNF component, and this particular image is showing the pure pixels locations in the data. Now, in this case, we have used this ND visualizer where the pixels are moved in this n dimensions, and these are the MNF components which we have used for the extracting of n members. So you can see here, whenever these are coming at the extreme, we are extracting as the class. So these are the pure n members extracted for different classes. So normally whatever coming at the extreme, that's why it is called as end member. End member means whatever coming at the extreme of that particular feature. Like suppose if you have two class, then it will appear in two corners of the line, two edges. If suppose there is a triangle, so whatever vertices are there, so in that corners they are considered. So they are the three different pure classes. But if it is coming in the edges of the line, so it means they are mixed class. Now coming to the classification of hyperspectral data. So as I told, that unmixing and classification. So I'm going to explain few techniques, but there are many many techniques for classifying hyperspectral data. So spectral angle mapper, spectral feature fitting, and subpixel technique, that is for unmixing, that is linear spectral unmixing and mixture tune match filtering. So a spectral angle mapper is a spectral similarity measure technique. In that, we are measuring the spectral similarity between the reference spectra and image spectra. And angle between the two spectra is used for measure of discrimination. So you can see here, this is a reference spectra, and this is two spectra of two targets, that is object T and object K. So you can see here the angle of that is being calculated by using this equation, where phi is spectral angle. Here it is E is image spectra, and R is reference spectra, and N is the number of classes. So whichever N member, whichever particular object have minimum angle, it will go to that particular class. Now, this particular classification technique have one more unique advantage, because it is insensitive to illumination variation. Suppose this is your from dark and this is too bright. So what is happening is, if suppose some object which is in the shaded area will have low reflectance, will come here. And suppose some object, they are formed as a vector, and some object which is in the illuminated area will have high reflectance. So it will lie in the same vector. Okay, so whatever is in the darker side, that will also classify to that same class, and whatever will be in the brighter side, that will also be classified as the same class. So now variation in illumination will not affect this particular classification, and you can see how this particular image got classified. And here when we use maximum likelihood classification, this particular area got unclassified. Now in this particular case, we can generate two types of images. One is colorful classified map, and another ruled images for different particular class. So you can see here, darker pixels are more similar. So here you can see grassland is appearing dark. This is near to the Forest Research Institute of the Dehradun area. And this forest area with near below to that FRI is appearing dark here. And below to that, the urban area is appearing dark. Now coming to the angle, here whenever we are taking different angles like 0.02, 0.05, 0.1 radians and greater than 0.1 radians, you can see when 0.05 radians was taken, fewer pixels got classified. Increased to 0.05, many are unclassified. 0.1 radians, almost all the classes got classified and few classes got misclassified. And when we increase the angle greater than 0.1, most of misclassification is occurring here. Now, another classification technique being used is spectral feature fitting. So in this case, what we have to do is, because here reflectance curve is important, and most important here is absorption. So what we have to do is we have to compare the absorption feature of that particular image spectra and that reference spectra. We have to compare that. So depth of that particular absorption feature is being compared, and shape of the feature absorption feature is being compared. So by using that, we can identify that particular material. So that in this case, this is a Cuprite Nevada data, Everest data, which is using the short wave infrared region. So here, when we classified this for alunite minerals, so wherever alunite is there, they are appearing bright. Now coming to the unmixing. So first we have to understand there are two types of unmixing, linear and non-linear unmixing, linear mixture and non-linear mixture. So here linear mixture is what? When from sun, incident ray is coming and reflected ray is going from the object separately, then they are considered as linear mixture. Non-linear mixture is when the mixture are intimate, then the response coming from a particular object will be mixed. So here you can see these are the material which is mixed. The C is the mixture of 60% of A feature and 40% of B. So you can see here how this material is appearing in case of C. So the absorption which is not visible in A will be visible in C because of the absorption present in the B. So this particular mixture of that material can be detected in your hyperspectral data. So here you can see how do we know that. So first we have to understand, suppose three mixed features are there, A, B, and C. So here A is containing 25%, B is 25%, and C is 50%. And they are lying, absorption positions are at different wavelength position. When we combine that particular three material in a single pixel, you can see how the spectral response curve, spectral reflectance curve of that feature will appear. So whichever will be having more domination, the absorption feature of that will be more dominant. So coming to that unmixing technique, so normally we have to go for spectral unmixing and we have to generate different score images for that particular hyperspectral data. So it generates the relative abundances of materials depicted in the image. Reflectance at each pixel of the image is assumed to be a linear combination of reflectance of each material present within the pixel. So here, this is the reflectance of different bands. This is the reflectance of different particular material, that is end member, or you can say spectral reflectance curve of the various feature. This F is representing the fractional coefficient or weighted fractional coefficient of that particular target. So in this case, we have to see that number of end members must be less than the number of spectral bands and all the end members in the image for an efficient mapping result. So whatever features which are present in that end member should be there, which should be less than number of bands. Now, normally what happen here is we can constrain the fraction to sum to 1 by adding another linear equation, that is Fi is equal to 1. Means the value will range from 0 to 1. And this is called as partially constrained case if it is not, and we can further constrain all the fractions to be between 0 and 1. So whenever it is between 0 and 1, it is fully constrained. So whatever value which are appearing darker, like in this case, vegetation spectra was taken. So vegetation is appearing bright, means it is having high score, and rest of the features are appearing dark. It means it is having 0 score. In this case, you can see water bodies highlighted here with high score. In this case, dry river bed and some of the urban features are highlighted with high score. Now coming to the another unmixing technique that is called as mixture tune match filtering. Now, in earlier case, it was full unmixing technique. In this case, partial unmixing technique is it is a partial unmixing technique. In this case, user-defined end members can be given. Like suppose we have to classify only urban, or we have to classify particular vegetation. Then we can give that end member to that, and wherever it matches in the image, it will filter out. That's why it is called as matched filtering. So in this case, we are filtering, we are matching with the end member, and we are filtering out that particular end member. And in the mixed pixel also, it is doing that particular filtering, and whatever abundance value or weighted fractional coefficient values are there, that are getting calculated. So normally it is generating the score images ranging from 0 to 1. 1 is considered to be the pure class and perfect match, and 0 is no match in that particular class. So here, because of that, that's why it is called as mixture tune match filtering, because in this case we are considering additional parameter, that is infeasibility, where when we have high score and less infeasibility value, that means that is the class. So here you can see when we plotted the scatter plot between a score image and infeasibility image of urban area, you can see dry riverbed is also appearing bright. But here, when we consider that high score and low infeasibility value, only urban area got highlighted. In this case also, when we consider that, then vegetation class, whatever we have given, is only highlighted. Now coming to the softwares which are being used for hyperspectral data processing. So NV has full-fledged module for this hyperspectral data processing. IIRS Imagine is also having hyperspectral module. Multispec and BIM are softwares for hyperspectral data processing. Different applications, for which application they are being used: vegetation, soil studies, mineral mapping, water quality, snow grain size studies, urban studies. So this I'm going to tell a few of the examples of that. So for vegetation, normally it is used for evaluating vegetation stress due to natural agents, drought, disease, insects, due to air and ground pollutants like trace metal and acid deposition and ozone. Species diversity mapping can be done, crop canopy biochemistry can be done, crop growth models and yield prediction can be done through your hyperspectral data. Now, in this case, these are the three data sets from Landsat 7 ETM plus 6 band, 9 band, and around 150 bands data. So you can see here the vegetation species which are misclassified over here in the multispectral data got classified properly in your Hyperion data. So how we are able to do that, you can see through the this example. The spectral profile here for different species are separable in different bands which are getting classified over here. But in case of this, misclassification and false classification is happening over here. Now we can go for hyperspectral data simulation also, if suppose we don't have hyperspectral data. So this work was done by one of my student. So here we can see that we have simulated 70 multispectral bands from advanced land image and multispectral data with the help of ground-based spectra and your multispectral data. So you can see the spectral profile are appearing more or less similar in this particular case. Then this is the classified image generated for the same area. So wherever that misclassification is happening in multispectral data, when we classified through hyperspectral data and simulated, they are quite comparable. Then this is being used for soil studies, like you can see a study about the moisture content present in that organic features present in that. So you can see here how the spectral signature is varying. And here we have used Avery's NG data for classifying the red soil and black soil. So here what we did is, when we classified through your normal atmospheric corrected data, and when we used MNF based data, the classification got improved because the noise content got reduced. So whatever black soil are getting misclassified over here got classified here properly. Then mineral mapping can be done through your hyperspectral data. So you can see here the hematite, montmorillonite and pyrrhotite got classified over here. So how it can be classified in Rampura Gucha mine and Purbanera mines, you can see. Then water quality studies was done in Hyperion data, and same thing was used for classifying your every Senji data. So the different locations, in this different locations, spectra were collected, reflectance spectra were collected from ground spectroradiometer, and then turbidity was calculated for different area. So you can see how the turbidity is varying for this Chilika. Then snow grain size mapping was also carried out. You can see how the grain size is varying with different spectra and how the grain size got classified with different area. Then we can also go for single frame super resolution, like every Senji data, which in this case was used, is with 8 meter spatial resolution. Now when we did the resampling, so this kind of data was generated, and when we processed single frame super resolution to enhance the spatial resolution to 4 meter, so you can see here this area was misclassified. But when we did the super resolution with different technique, you can see this was classified as soil feature. Now coming to the material identification using ground-based hyperspectral data. So in this case, close-range hyperspectral data was used, and we used reflectance-based, MNF-based, and we have selected few of the parameters, extracted few of the parameters from the data. Then we have done the classification. The classification of those features got improved with the use of various parameters. Then we can do the integration of LIDAR and hyperspectral data for classification. So here you can see this particular area with the different vegetation species got classified, but some of the urban areas are unclassified in these two cases. But when we use the LIDAR data information, means when there is a height variation, then it was unable to classify. When we use this LIDAR data, we integrated that, then the urban area got classified properly. Now, limitations of hyperspectral data is it is difficult to interpret spectral signature of an impure pixel. Because of high spectral resolution, a fine atmospheric absorption feature will be detected, so which may be confused with the ground material being imaged. Data volume, size of IIRS data is 40 times with thematic mapper. So you can think of, if we have hundreds of bands and if we have only 6-7 bands, how the weight of the storage of the data will be high in that case. Redundancy, overlap of information content over several bands. So some bands are spectrally overlapping also, like because some of the sensor which is with VNIR and SWIR, so the common wavelength ranges are being also observed. The spectral reflectance of a mixed pixel is generally the weighted average of the spectral response of the classes within it. So you can see this kind of mixed pixel responses will be there. If you have many number of features present in a single pixel, it is very difficult to identify. Future scope is ultraspectral, which is called as beyond hyperspectral. Normally, it will contain thousands of bands ranging from visible to reflected infrared to thermal infrared region. No such imaging sensors are there. So this is considered as future of hyperspectral remote sensing. Thank you.